Hi, everybody. My name is Michael Wong, and I'm a distinguished engineer at CodePlay. And today I would like to talk about modern embedded software needing modern C++ programming. So just a slide that summarizes what my company does and the products that we offer. One other thing something about me. I am a distinguished engineer at CodePlay. I chair the CppCon heterogeneous programming language, as well as the C++ directions group. In my career, I switched from high performance computing to working now with embedded systems through my company that provides services for programming embedded systems. So in a way, but in so doing, I've also switched to machine learning and covering AI. That's why I'm chairing SG19 and SG14. But in so doing, I feel like I've really come full circle because there's some aspects of embedded programming that is completely high performance computing these days because of the machine learning that's done there. And because we do a lot of things with autonomous vehicles, self-driving cars, making them safe. So that's why I'm trying to collect some of the experience that I have from working in this field for me, as well as my years in the past of chairing SG14, benefiting from many of the people that's been involved. So as a result, I want to say that many of the slides comes from probably unconsciously, consciously watching some of the talks that have happened and listening to them through SG14 and within my company. So I even lifted this disclaimer and acknowledgement from one of them. I don't remember who. But however, I would want to make sure that any credits for any errors are all mine. They're all mine. You can't have them. So just the usual disclaimers that we're going to refer to some company products and things like that, and they all have their own marks and that you should refer to them. So let's start. So this is my 3-act play. So what is embedded? How to change from C to C++ and why? And modern embedded C++ programming. And I'm going to summarize what SG14 has contributed to C++ and where it's going. So let's start with the first one. What is embedded? So this actually is not a good picture for what is embedded. There are many pictures that come afterwards. I've been told that in any talks, it never hurts to have pictures of cats in there. So this is just me trying to sleep with my cat. So it has nothing to do with embedded, but this does. So what is an embedded system? So people have always struggled with the definition of an embedded system. And I'm not going to claim that I can do any better. All I can say is that it's a wide range of things and nobody really knows what it is. It goes from the small to the large, the few to the many, and I'm going to go through some of that just to see if it hits some of your nerve points. So an embedded system is pretty much nearly any computer other than a desktop, laptop, or mainframe computer. And there is a definition, and it says that it's a combination of hardware and software, which together form a component of a larger machine. It's a combination. So an example of an embedded system is a microprocessor that controls an automobile engine. And this embedded system might be designed to run on its own without human intervention and may be required to respond to events in real time. So computers we do know that it is definitely a computer that's used as part of a larger system. And here, and the thing is, they don't often look like a computer. They look like physical devices. And often reliability is a key. It's critical as in if the system fails, someone might die. So, and the other thing is that resources might be limited. So in other words, it's basically any sort of device which includes a programmable computer, but itself is not intended to be a general purpose computer. And how many do we use? Well, the average middle class home has roughly 40 to 50 embedded processors in it. Okay, that's in the microwave, it's in the washer, hairdryer, coffee maker, remote control, humidifier, heater, toys, etc. If you have a car, for instance, it probably has about 60 embedded processors in there, in the brakes, in the steering, in the windows, in the locks, ignition, dashboard, display, transmission, mirrors. Even the mirror might have it. Personal computers, if you think they're not embedded devices, you might be wrong. They might have over 10 embedded processor in there, in the graphics accelerator, in the mouse, in the keyboard, in the hard drive, CD-ROM, bus, network, interface. Okay. So It is many things, and often it's purpose-built. And there are many people who think it's one thing, but it's definitely not. It's a wide spectrum. And I know enough to say I don't know what it is, and that I occupy a very small part of that. Computing systems embedded within, it's basically the computing systems embedded within electronic devices. It's really hard to define. Nearly any computing systems other than a desktop, and there are billions of these units produced yearly versus millions of desktops, maybe 50 per household and per automobile. And they span a wide range of seriousness, from fun, pure fun, like a little Raspberry Pi, to deadly serious systems that is controlling nuclear reactors or vehicles. They might span a wide range of response times, from microseconds to milliseconds to seconds. And this is touch on the idea that that you have this thing about some of them might be hard real time that are designed to meet all design deadlines, and a missed deadline is a design flaw. They might be firm real time, which is designed to meet all the deadlines, but occasionally they might miss deadlines and is allowed. That's allowed. So the system is designed to meet basically all deadlines, but occasionally a miss is okay. And sometimes they're statistically quantified. Examples of that are like multimedia systems, hardware designed for average case performance. Then there's soft real time. That's designed to meet as many deadlines as possible. The system is designed such that it uses the best effort to complete within the specified time. But it might be late, for example, a network switch or router, okay? And these are some of the things that we have to deal with. Other things is that there are plenty of other things that's critical is that predictability might be key. Correctness is even more important than usual, okay? They also span a wide span of replications, from single ones, like maybe a nuclear reactor, to millions of toys that might be in production. And these are different ways that they could be produced. They span a wide range of hardware also, from 1 kilobyte to 1 megabyte to 1 gigabytes, 8 bits, 8051 PIC AVR, where there's no full C++ standard that can work in them, 16 bits, MSP 430, PIC, or 32-bit from ARMS, MIPS, Tensilica, Intel, or even 64 bits. So in the 64-bit, the types of embedded processors for computational micros, like 3264 bits data paths, they might be CPU or workstation, of the CPU of the workstation, PCs, or high-end portable devices like PDAs that is using x86, PA-RISC, PowerPC, Spark. They might be embedded general-purpose micros that are 32 bits, designed for a wide range of embedded applications. They're often scaled down versions of computation micros. These are available from ARM, PowerPC, MIPS, x86, 68000. They might be microcontrollers that are 4, 8, or 16-bit data paths with integrated processing unit, memory I/O buses, and peripherals. They are often low-cost, high-volume devices. They might also be domain-specific processors with varying different data paths designed for a particular domain, with digital signal processors, multimedia processors, graphics processors, network processors, security processors. And these days, there might be AI or machine learning processors or tensor processing units, which is the kind of things that, that my company programs for. So they definitely span a wide range of supported software, from bare metal, where there's just a library, but there's no supported OS, no separate OS, to interpreters that have maybe a real-time operating system, to desktop OSs that are Linux or Windows. So in general, I separate them into two general domains. They're the megabytes, the gigabyte, gigahertz, multi-core memory with memory latency caches. These are good for high-frequency trading, gaming, simulations, large embedded systems. To the small bytes, kilobytes, they're running at megahertz, interrupts, hardware. These are like the hardware peripherals. And in that space, battery lifetime is an issue. So in the small embedded systems. So some embedded characteristics, definitely they probably have application-specific functionalities. They specialize for one class of applications. They might be deadline constrained in that the system have to perform its functions within a specific time period to achieve a successful result. They might be resource challenged in that the system typically are configured with a modest set of resources to meet the performance objectives. They might be power efficient or need to be power efficient in that many systems are battery powered and might have to conserve power to maximize and use the usable life of the system. They might have form factors where many systems are lightweight and low volume to be used as components in whole systems. They have to be manufacturable. They have to have manufacturable qualities, like they might be usually small and inexpensive to manufacture based on the size and low complexity of the hardware. In terms of design, as we work closely with some of the design before they hand it to us to program them, we notice that they are certainly concerned with things like unit costs, which is the monetary cost of manufacturing each copy of the system. They might be concerned with NRE or non-recoverable engineering costs. This is the monetary cost of manufacturing each copy of the system. Okay, this is the one-time monetary cost of the design of the system. Okay, they might be concerned with the size, the physical space required by the system, the performance, the execution time or throughput of the system. They might be interested in the power, the amount of power that's being consumed. They might be concerned with flexibility, the ability to basically change the functionality of the system without incurring heavy NRE costs. They might be concerned with time to prototype, the time it needed to build a working version of the system. They might be concerned with time to market, the time that's required to develop a system to the point that it can be released and sold to customers so they don't miss a peak point in the market when it's needed. In terms of, they also would be concerned with maintainability, the ability to modify the system after its final initial release. And then furthermore, they might be certainly concerned about the correctness, the safety. So in terms of dependability, they might be interested in reliability. That is the probability of a system working correctly, provided it worked at time t equals 0. They might be interested in maintainability. That is the probability of a system working correctly, certain time units after an error occurred. And then availability, the probability of the system working at time t. Safety and security in communications, basically critical applications have to operate correctly at all times, like airplane flight control computers, and this would include both hardware and software aspects. So who are the embedded programmers? They certainly come from the domain of professional programmers or engineers that would know programming training and everything in between. There's definitely a trade-off, okay, in that the expertise, they need expertise with both software and hardware is basically needed in both the optimizing the design and the optimizing the subsequent programming. So a designer of this has to be comfortable with various technologies in order to choose the best for a given application and constraints. So complexity is increasing. The code component of the system is increasing. The complexity of the code is increasing. And you need change, the needs change over time, and that's increasing. We need all the help we can get, and we all need to get better at handling code complexity. It's harder to, typically I've found that systems are becoming more complex, it's harder to think about total design, and it's harder to fix bugs. It's harder to maintain the system over time. So therefore, the traditional development process has to change. The traditional development process in embedded programs seems to be that you would restart everything, and that's not necessarily the best way to do it. And that's kind of the point of this talk, is that switching from that mentality to from C to C++, where you would use a more designed life cycle, an overall view of the design before you get down into coding. Okay, so let's talk about C++. C++ is a multi-paradigm language, and there's no excuse basically to add incompatible parts. Some of this is from our slides from the C++ directions group that I'm part of. And so today, we definitely combine aspects of object-oriented programming with generic and functional and imperative programming, but trying to still provide a kind of coherent style of use. We definitely rest on two pillars, a direct map to hardware and zero overhead abstraction in production code. And we don't want to fall into the trap of abandoning this path, which can seriously jeopardize compatibility. And we don't want to stop addressing new challenges like higher level concurrency models. And if we fail, developers are going to switch to some other framework to gain better performance. We want to strengthen our two pillars of supporting modern hardware, as well as more expressive, simpler, and safer abstraction mechanisms without adding overhead. And this has been a rule within C++ in that we don't want to leave room for a language below C++. We want, and to do that, we want to have more useful abstractions so that in principle, the C++ standard library can be implemented in C++ plus a few intrinsic operations for accessing the low-level machine facilities. We want to have no memory corruptions and no leaks because C++ relies critically on static type safety for expressiveness, performance, and safety. So the ideal is complete type safety and resource safety. In terms of domains, C++ is now used in more domains than ever. We don't specifically recommend any specific domain, as every domain is important to somebody in the larger C++ community, even if their domain isn't well represented in the committee. But we do intend to broaden our support for domains that are well represented, and even non-traditional ones. So here we list a few, like domains of safety and security, simplifying C++, interoperability, demanding applications, embedded systems, and alternatives for error-prone and unsafe variants. So one of the things that I've noticed is that the constraints on the embedded code differ, and this is in discussions with Biana, in that different kinds of systems require different styles of usage. So big systems might use the full language. Big systems with real-time constraints might be able to use the full language, except on the critical path, so that you can use the predictable subset of C++ on the critical path, like avoiding the free store, dynamic, such things as dynamic memory of the heap. Small safety critical systems might also use a predictable subset of the C++. Tiny systems that are 8-bit might use a subset of C++, but preserving the zero overhead. And small 4-bit systems, they might not have a C++ compiler, so they might actually have to stay in C or assembler. But in most cases, you want to optimize memory usage because space is time here. So that completes the first act. The second act, I want to talk about how to change, for those of you guys, a kind of a practical handbook on how to change from C and C++ and why. So there are some good reasons to stick with C. I'm not bashing C because I want to try to give a reasonable comparison of what they have. You might have no C++ compiler available, and this is probably the case in very, very small systems. But even those are beginning to come with C++ compilers. You know, if you have an ARM5, is C but not C++, but ARM6 in 2015 is Clang-based and fully C++ 14, and will update to C++ 17 and enable things like LTO. GCC obviously targets many embedded devices. If you have something like an 8-bit, less than 1K controllers, that might be the case that you can't have a C++ compiler. So basically very small, no OS, real-time programs without communications. You might be the case that C is required or mandated by older standard customers, law or safety or standards or insurance. So for that, something like classic AutoSAR has to follow C. But I noted that even AutoSAR, especially the adaptive AutoSAR, which is fitted for parallelism, is now switching to support C++. You might have an Infineon RX that has a lockstep multi-core processor for safety critical system. But even there, think and ask for modern certified compilers there, and you might have it. You might really need variable length array. Who needs that? And if you do, well, only C99 has it. And that's now actually optional in later C. It is not in C++. You might also, so I would say that as a result, almost all new chips now benefit from C++. Any of the ARM-based 32-bit microcontrollers, any of the embedded Linux, RTOS, even the Arduino is C++. there might be temporary reasons that you might need to stick to using C. You might have no guidelines, and you have no training or education in C++. That's why you're here. There's lots of internet video on C++. Much of all of this conference goes on are freely available on YouTube. You're coming to this conference. You might use Misra C++, or you might use C++ core guidelines. Your staff might have no C++ programmers, which might be a surprise because many graduates these days want to program in C++. So again, get training from many of the trainers that are available here at this conference and internationally. You might have a very large C code base and you want to really stay with that. And you would, in that case, you might have to start with compiling your C to C++ code. In most cases, you just have to change .c to .cpp, turn on the C++ mode, and you'll probably get lots of errors with voice style conversions. Then you're going to have to look at each and every one of these and basically change them to their real type. So many previous speakers to me have talked about some of the myths about why not use C++ and why not argue with people. I specifically refer you to Dan Sack's keynote a couple of years ago. The myths comes fast and furious in that people would say that C++ is complex and large. But I would argue that, as I said in the fireside chat earlier, you don't have to learn all of C++ to be productive. And I think SG 1440, 20, our education group, is going to try to show some reasonable path through that. I myself don't know all of C++ either. I don't think anyone does. Or if they say they are, they're probably lying. It is a large language, and it's not easy to keep up, even for us committee members. But we do the best we can, and I'm still productive with C++ without knowing every detail. C++ makes code execution less predictable debug. So that's kind of like what most electrical engineers hired to do embedded programming will say, because they love C style, and they think in assembler almost immediately when they're writing C code. And vendors, as a result, tap into that thinking, and they love selling them debuggers and generators. Computer scientists, however, like C++ in general and loves to build and use abstraction so that they can get into that write, review, test cycle. You might say that C++ is changing too fast. Yes, that is the case. It's changing every 3 years. And yes, we're adding lots of features that is further helping, as a result, that's helping embed it and safety critical. While C is not changing, at last I heard, they're still on a kind of a 10-year cadence. So some bad reasons about why not use C++. Some people might say that we worry that we can't change back to C. The idea there is that you could do it gradually, and I'm going to show you some of those steps, and don't go all the way to what I call the third age, which is like meta programming. If you go gradually, you there for a moment. Okay, we're back. So you might worry that C++ is slower, and hello world. Let's see if I can get back my screen. Okay, so you might worry that C++ is slower. Hello world is a bad example in my view. In the embedded world, I don't really see too many cases of printf and stdout being a fair comparison. They're probably not that relevant. Okay. So C++ produces large executables. That's another bad reason, I think, in terms of arguing why you won't use C++. You have to use your tool chain properly in that case. You might say that you don't have the right people. The C-style electrical engineers or C++ computer scientists are both not quite right. Okay, I know that my video has disappeared. It's going to come back. Excellent. All right. Next. So there was a poll that was done a couple of years ago by Patricia asked about one for C++ and one for C. And they asked, what is the most common bug that you see in production? Others, so for C, the biggest bugs that people mention are memory leaks, that because it's not in C++ anymore because of RAII, and memory leaks essentially is not in C++ anymore because we have things like RAII, smart pointers, and raw pointers, and which are non-owning references. The second one they pick is null pointer dereference. The third and fourth is use after free and double free. I bet you're wondering what are the biggest problems in C++ that they think from this poll. The biggest problem in C++, they claim, are null pointer dereferences, which are now, I would claim today, 100% avoidable in terms of unique pointers, containers, values, references, checks, and you might use the GSL not null or MISRA. As long as you just use no plain pointers or C array, you should be able to get around this. In terms of memory leaks, which was the second problem, think about using RAII, okay? And use it. They also mentioned use after free and double free. And finally, dangling is something that still remains a problem that is in C++, and we are definitely working on it. So what do people think and what do people think what C++ is? There are many things. I kind of like to separate out into 3 ages for embedded programmers so that when they want to progressively move into C++, they might choose to go slowly rather than go whole hog into something like the 3rd age, where we're talking about meta programming. In the 1st age, it's mostly object-oriented style programming, and that's kind of the things that you'll see, putting things in containers, encapsulating their safety. Dan had a great talk yesterday that talks about how to build that into a memory map, and then after that, you might or might not move directly into the 2nd age, where we have things like template meta programming. And these days, most of the advice after this I'm going to show is that you probably should skip that and go directly to the 3rd age. So today, the modern C++ with 2nd and 3rd age, there's deterministic object lifetimes, there's scope, there is templates for variables, constants, there's standard libraries, there are compile time programming and flexibility, there's type safety at compile time, we have const expr and const eval coming, and SG7 is rapidly pushing more of the envelopes of meta programming, where programming doesn't look like it's a template. There are no angle brackets in sight. And SG14 is working with embedded and low latency to improve that, as well as potentially adding safety through SG12. So comparing C and C++, the way I think about the difference is that in C, the programmer takes and has full responsibility. It has a limited type system and the conventions rule. So it has basically simple code generations. It has single global scope, except in local variables. It might have arbitrary memory interpretations through casting. It might have undefined behaviors for optimizing capabilities. For C++, I would say that the compiler generally can guarantee type correctness and can give you efficient code generation and optimizations. It has a very effective standard library, though some of that you might not be able to use. I'll talk about that. It's a multi-paradigm language, but it does inherit holes from C compatibility, which ISO C++ is trying to erase by substituting with safer features. So it's definitely a change in thinking. For the most part, C and C++ use static data types. So that is the case where an object's declaration determines its static type. So here, int n is a signed integer. A double d is a double precision floating point. Char star p is a pointer to character. So an object's static type and an object's static type doesn't change during program execution. It doesn't matter what you try to store into the object, the type won't change. This is important in terms of thinking about what's a data type. In C++, unlike C, a data type is a bundle of compile time properties that includes the size and alignment, a set of valid values, and then a set of permitted operations. So in a data type, like on a typical 32-bit processor, a type int has size and alignment of 4 bytes. It has a value from this very small negative number to this very large positive number inclusive. And in the intervals, it only picks the integers. In terms of operation, this is one of the key points. it allows these particular unary and binary operations. So what's so special about that? Well, it's more about what it can't do. A data type can't do is what's important here. Here, an integer cannot do indirections like it's a pointer. It can't do member selection. It can't do calls like a function. And this is a huge difference between C and C++. C++ is going to reject at compile time all these questionable operations that C is going to accept. So to summarize, in C, you, the programmer, takes and has full responsibility. There's just no runtime checks provided by the compiler. So you can have null, dangling pointer references, out-of-bound array, arithmetic overflow errors. It is your responsibility to acquire and release resources and check for errors doing so. So doing things like malloc, open, create sockets, or fork. And the compiler basically trusts your typecast. And so I understand why the attractiveness to C. Yes, this gives you with great power, but it obviously puts a great deal of responsibility on you. In C, the conventions rule. So with strings, it's always these null-terminated byte strings. That's literals are basically char arrays. String XXX functions have inconsistent conventions, like string ncat copy and string ncats. The caller might need to free allocated memory, okay? And the caller definitely need to provide large enough buffer, like getS or sprintf. And the functions might have global state, like static variables, like string toke. C also has a limited type system. It has implicit numeric conversions that are intricate rules for integral promotions, that are silent truncations and expansions. They might have undetectable overflow, and enum types are just casts and ints. And there's also array to pointer decay in C. Finally, there's type pruning, and casts are almost unlimited. A type def doesn't define a new type, but struct and array definitions construct new types. And void star is a generic parameter type. Now, I know there are questions, and I'm going to address the questions at the end of the talk. Thank you. So the problems of C as a language for larger systems is that it gets even worse in terms of the limited scoping. There's one level of global scopes of global names, and you use macros for genericity. So there's no overloads, no namespace pollution, reuse limitations, and pretty strange naming conventions, in my opinion. There are many undefined and implementation behaviors, often that are not well understood. Pointers are essentially required everywhere and cannot easily be distinguished in terms of validity, ownership, and lifetime. So why use C++ and instead of C? Well, in C++, by contrast, it has a deterministic object lifetime, no more resource leaks. Since C++ 11 introduced transfer of ownership semantics, aka move semantics, and unique pointer. There's strong user-defined types like that are distinguished and encapsulates, like so that you can have no unwanted conversions or narrowing, distinguishing parameters to avoid the long calls, and enables overloading and template argument deductions. In the standard library, there's no more need to debug handwritten loops. You should use algorithms. There's no more need to manage memory using containers like vector of t or string. Though standard library do have a caveat, which I will mention later on, in terms of the fact that they do use the heap. And in embedded programming, they prohibit the use of the heap. So there's more efficient programming, less explicit, and more efficient code, which are better optimizable. More details about why you C++ instead of C. There's encapsulation of dirty system details like parameterization of system dependencies. There's a strict type system for compile time safety. I talked about that. There's no need for plain pointers or arrays or explicit memory management. And there's reasonably efficient code generation, especially through templates and things like return value optimization. And there's no overhead with the return by value. So let's take a look at modern C++, embedded C++ programming and SG14 in the remaining time that we have. So how do you change a C code base to C++? Well, there are pretty much two ways that I've observed and have helped people with. There's one that's switching in one shot, And then there's also gradual adoptions, which I'll walk through some of the steps. So let's say you want to switch in one shot. So if you do that, there are C++ features you probably might want to avoid, things like RTTI, use of the heap, exceptions, standard containers, except unique array and unique pointer and standard array, and floating point. Let me talk about what these might mean. Okay, so there's things in the C++ library that you have to be aware of, like extra space allocated on the heap. The integer calculations are done using int. Floating point calculations are done in double. Their special situations are reported by exceptions, and caching determines speed. So avoid linked lists. So all that matters is basically amortize complexity. The problem with the heap, let me talk about that. The heap is flexible for the amount of data at the cost of unpredictability in runtime and fragmentation due to the maximum memory available. And heap and small embedded systems don't match well. They generally do a rigidly prescribed task with fixed data. They might need to meet real-time constraints, and it has to be met always and not just sometimes. So in that case, it's probably better to use global allocations or fixed size pool or fixed size container. The problem with the floating point I mentioned, this is useful when a wide dynamic range is needed, but small embedded applications often have very small, well-known ranges, like small microcontrollers often don't have floating point units, just a software floating point, which resides in the ROM and is painfully slow. This is not true for large embedded systems, so this rule is not necessarily the case for all embedded systems. In these cases, it's better to use a template with a default parameter of double, which can be used if there is a floating point hardware. The problem with exceptions. Well, exception is basically used to handle local problems that requires a global response and often uses the heap. Making it slow in the non-happy path and predictable. You're wondering what the non-happy path is. Happy path is when there is no exceptions and the code run all the way through. The non-happy path is when there's an exception. So small embedded systems have a rigidly defined task with no exceptions, just different situations and no heap. In these cases, you're better off to not use exceptions until its implementation uses the stack instead of the heap. This is an SG14 project where we notice that there's nothing in the standard that stops you from implementing exceptions by using the stack, a stack-based exception. It's just that traditionally we have always implemented exceptions on the heap, which generates dynamic memory allocations as well as multiple large table generations, which causes the non-determinism. So we're trying to improve that. Basically, I want to conclude that C++ needs both error code and exceptions. There are places where you need error codes and there's no shame in using them, okay? There are places for exceptions that you can't get away from, like constructor failures, like operator failures, like callbacks. The only way to report error through those is through exceptions. But there are many other places where error code is useful for if you have a space restrictions, like small systems where exceptions can support can crowd out the functionality, where you have a hard real-time system and we don't have tools that so where exceptions can cause non-determinism. So the next strategy I want to talk about is the gradual adoption strategy, which is what most people should think about. Because C is mostly just a subset of C++ with a few exceptions. You can find what the compatibility is, I think, in Wikipedia, as well as in isocpp.org. You can compile your C source with C++, as I mentioned before, change your .c to .cpp, resolve issues with linker naming due to the name mangling of C++, watch out for void star conversion errors and change them to the actual type. Start walking through these different impact strategies. So there's a low impact strategy that won't disturb the C culture. It's basically almost C like C++. There's a medium impact strategy that you might expect some resistance in your crowd. And then there's the first age, the object-oriented, and STL, that's starting into modern C++. That's familiar to C++ programmers. Then there's the second age with template metaprogramming. That is even more modern C++. But you need experts on hand, and I will admit that without those experts, you're likely going to go somewhere else. And then finally, skipping past that is the third age, metaprogramming, using const expert and no angle brackets in sight. So let me walk through at least a few of these. I don't think I'm going to have time to walk through all of them because these are separate talks in themselves. And there are other talks that will cover those much more nicely. So let's start with low impact C++ features. You can use these low impact C++ features, I think, without any serious degradations. These are like assertions with static asserts and type traits. Use C++ bool, not your own Boolean. Use brace inits to prevent narrowing. Do unit programming. You would either user-defined literals or something else, or templates. Be fast with generalized pods. Use unique pointer. That is explicit ownerships. Use arrays. That is slim and fast. Use move semantics. That's a cheap way of moving. Perfect forwarding that preserves L values and R values. Use default and deleted. Use the no discard angle bracket, square bracket attributes. Use const correctness. Use binary literals. Use the quote, the separator in literals. Use namespace. Use enum class. Use by reference parameters. You can evaluate a compile time with const expert instead of macros. Use if const expert. You notice that these features span C++ 11, 14, 17, and into 20. So there are lots of features in C++ they can use as a low impact way. I'm just going to go through some of these. I'm not going to go through all of these. We probably don't have time for all of that. But yeah, brace init prevents narrowing. Here we have a double, and you can say in A is assigned this double, and that's okay. Okay. You might use the function initialization syntax, but if you use brace initialization, that's an error. That's non-compliant right away. That's a good thing for us. Okay. You might use static assert and type traits. Type traits basically perform at compile time type information, type comparison, and type modification. I saw a really good talk yesterday by Jordy about type traits. I thought it was really nice. You can use static assert to validate the expressions at compile time. Okay, and some examples on the right that shows that. You can use user-defined literal. I'm really proud of this feature because I kind of created it myself with many other people to help. With this, I'm just demonstrating here that you can using a syntax with a built-in literal with an underscore and a suffix, and that allows you to create things like, actually that should be a binary literal, 101010 underscore B. You can create a floating point literal that is like 123.45 underscore kilometer, and this will be type checked because these have specific literal types. You can create a string literal. You can also create a character literal. Okay. You can generate fast generalized pods today, which are very similar to what C has. These has to be trivial. They have to have standard layout members. Have standard layout. They have to have members and base classes that are not also be pods. So they offer fast manipulation, like a C struct. Arrays of pods can be copied by block, and they can be statically initialized, which takes away some of the worst problems that comes with dynamic initializations in the original types. You can have you can access fast and slim standard arrays using homogeneous containers of fixed length. That combines the performance of a C array with the interface of a C++ vector with no heap allocations. Now, the problem with arrays is not really a standard C++ container type and has some characteristic that makes it not quite like that. But if you're doing interface with C, it probably doesn't matter. Today, we're beginning to come up with things that are much better, that behaves like a standard container type. They're called spans, and multi-dimensional spans coming that will help in this particular direction as well. You can use move semantics for cheap moving instead of expensive copying, so that you can improve your performance. There's no memory allocation or deallocation. It's like a pointer swizzle, so it's very predictable. You can implement safe move-only types with unique pointers, files, locks, and tasks. I'm going through these fairly fast because I know that you can certainly learn a lot more about these if you're interested in using it for your project through many of the resources, talks, or just looking at CPP reference, so that you know that these can be used without degradations. You can preserve L value with perfect forwarding. So you can basically pass the arguments while preserving the L valueness or the R valueness of the arguments. And the use cases for these are things like factory functions or constructors. You can chain a set of move semantics forwarding of move only types. You can certainly also enable explicit ownership with standard unique pointer, which gives you explicit ownership. These are only movable type, and they support arrays. So you can create and forget them. They're minimal space and time overhead, and they support special allocation strategies. You can use cons correctness very quickly. A cons is basically read only. So in C, A, B, C, D string is a non-cons char pointer, whereas in C++, is going to cause an error, while in C, that is going to be okay. You can use binary literals. This makes code a lot more readable, okay? And the base you choose convey a lot of information about the value. So something like 0b1011, I know you could have done it, earlier I showed that you can use _b, but the committee decided to go with a standard way of identifying binary literals, so by putting a 0b prefix on it, just like we do with 0x0b, that's a hex value, but not a quantity, it's not for calculation. Whereas 11 is just a quantity of 11. You can do oops, this is a duplicated slide, or unless I've gone backwards. Okay, you can use digit separators in literals. So numbers are hard to read with a large number of digits. And you might think that you can separate them by using the multiplication, but we don't know if this is going to be evaluated as a constant expression. So why not use 1'000 like this? I know that this is not the usual digit separator comma that you could have wanted, but we found out during the design of this that comma cannot be placed in a way that makes it readable by compilers. And as it turns out, actually apostrophe we found out is actually used as a digit separator in some countries. I can't remember which one right now. You can use namespace. In C style, you might use something that is like a namespace, but because you don't have namespace, you're forced to write something like mylib_myfunc. Whereas in C++ object-oriented style, you would use it as a class, so that mylib::myfunc. But the best, I think, is just using a namespace mylib and then calling myfunc within that namespace. You can do things like enum classes. So here it's not type safe. You have a color, that's an enum that has black, white, and red, and a chest color. And then when you want to paint by calling the white side, you don't really know, there's no error here. Whereas in a type safe environment, you will actually have to say that if you just call generic white, it's a compile error. But if you call something like chest : white with a paint, we know that's an error. But whereas if you call color : white, that's okay. You can call by reference. In the left, it's not entirely clear whether the star or the ++ takes precedence and binds more tightly to P. Is it the pointer that's being incremented, or is it the value that's incremented, the thing that's pointed to by the pointer? On the right, it's much clearer using reference parameters, because the reference is now hidden. I know for a fact that it's going to be the value that's going to be incremented. So learn to love const expr. These can be evaluated at compile time. They can be stored in ROM, like variables, functions, or user-defined types. Most microcontrollers have 4 to 16 times more flash than RAM. So flash values can't be accidentally overwritten. They can put everything in flash, and there's no runtime calculation and no floating point code linked in. That's one of the key problems that other people might find. So skipping past that, let's go to general adoption. The medium impact features are things like using shared ownerships with std share pointer, overloading, default function arguments, or transparent data types, or abstract data types for privates. I'm not going to go through all of these, but let's talk about share pointer. The shared ownership, it's for shared ownership. It has a reference counter and a handle to the resource. It manages the reference counter and the resource. And in managing and this helps you to manage overhead in time and space. It saves in memory. Okay, you do have to deal with any cycles. Overloading is in C. You would deal with it as something like you would have different functions for integer, double, and string. Whereas in C++, it's the same function that would be passed different types, and that would decide the overloading through overloading. There's default parameters. I'm going to skip past this. I think most people know what default parameter is. There's transparent data types. So here what happens is that we notice many errors in moving from embedded C code to C++, that they have similar types parameters very close by, so that you have X and Y integers here. And it's very easy to transpose those when you're calling a function, okay? It's better in that case to use a struct that encapsulates those very nearby parameters so that you can call lock, which and then incrementing X and Y by one for both of them. And that makes it a lot easier to be clear from transposition errors. You can use abstract data types that enables type-rich programming. I talked about that using user-defined literals so that you know what kind of units that you're doing. So in modern C++, you basically use head towards object-oriented and STL. That's the next step. And you can, for that, you can use class versus structs. They have very little difference in terms of costs. You can use decorators or adapters. You can use for : as a way to walk through ranges. You can use autos and destructors. Now, one question people always ask is how much of the STL can embedded systems use? Unfortunately, this is where some of the bad news comes. STL is mostly not usable because of the heap allocation and exception handling in that space, unless you can prove that it has deterministic worst case execution time results. With the exception that unique pointer has no overhead. And you can also implement by hand things like fixed size arrays, max size vectors, or flat map. Some of that is coming through SG14 as well as other groups, so that we can have more of these kinds of things that have no heap overhead, or something like boost intrusive container that has a metadata as part of the element type and no overhead. So the guidance is find the answer as much at compile time as possible and write type-rich code. Use resource management and RAII. In ordinary code, you can use most of C++ features and be able to use both error code and exceptions. There are some testimonials. Different companies have been able to move deeply into modern C++, like Sonova in Switzerland, move from C to C++14. Auto Intern, my good friend Odin in Germany, he is well into the second and the third age of modern C++, building embedded controllers using template method programming, using a library, an open library called Wasir. Kapernikov and the Ball Group have all made similar jumps that with large code bases. So in the future of embedded engineering is that you want to try to understand in C, you might do something like you try to understand the problem and you quickly program some solution and then you debug. In C++, you want to try to understand the problem, encode the understanding in automated tasks, and then to write the code implementing a test one at a time, and then improve the code, architecture, tests, and understanding until you reach a solution. This is, with modern C++ for embedded, you should be able to use things like encapsulation, naming of parameters, some algorithm, some scope-based resource management, like with RAII, with array and string view, if you have to heap, or unique pointer if you don't. Compile time parameterizations instead of macros, and using values and references or optional or smart pointers instead of using a pure pointer. So what's still missing for embedded? Well, we need good concrete guidelines for small systems use, and not just avoid malloc and exceptions. We need good semi-standard libraries that is less heap dependent, pool, stacks, standard containers. We need to understand that standard full C++ is usually good enough when you have anything that looks like an ordinary computer, whereas with something like example, like a PC or Raspberry Pi, we need to have more people from embedded help with SG14. And here I want to show what SG14 is about. SG14 is about embedded, which has number of chairs in there with Ben Craig, Wooten, Odin, Wouter, and John McFarlane. We also have other domains like finance, trading with Stefan, Carl, Neil, Matheus, Clay. We have covered games. That's our original Inception mandate with Renee, Guy, Paul, and Patrice. We also cover linear algebra with Bob, Mark, and Guy Davidson. Okay, so some of the features that we are working on. Ooh, I'm sorry, this is a bit of an eye test. We have actually injected two features into one in C++17 called Memory Management Facility by Brittany Freeman, and in C++20 on Likely and Unlikely by Clay Tritta. And unlikely essentially is the ability to say, in an if then else statement, or maybe even a switch statement, you can say which branch is more frequent, so that you can have the compiler organize code in a way that allows you to access them better. We're also right now working on some long pole items like enabling affinity. That proposal is slowly working its way through SG1, and it's actually looking really good. We've been working on system topology discovery to enable more ability to understand what your hardware, cache, and system looks like. We've been working, Ben Craig in particular, I want to call out to him, been working on improving the specification for freestanding. The freestanding section of C++ has been somewhat outdated by the fact that it's mostly still based on C from a long time ago and untouched by too many people. So we're hoping that this enables more legitimate official usage of the standard libraries and the language. We're working on linear algebra, adding things like BLAS, okay, and things that are ideal for machine learning. Working on executors with other groups, with SG1. We are working on things like intrusive pointers, deterministic exceptions, as well as exception that is stack based instead of heap based. Two I'm really excited about is Colony by Matthew Bentley, as well as Ring Buffer by Ingbar Levy, Matthew Butler, and Guy Davidson. There's Flat Map that's being worked on by Zach Lane. Renee is working on something called Members Layout Control, and there are other ones that's coming as well, having to do with debugs, exception handling, measurements. Okay, so I'm just going to skip past some of that because the rest is mostly about SG19. So what's next for SG14? It was created in 2015. We used the Proto Outreach Group, and it seems to have succeeded. We added features in C++ 17 and 20. There are more coming in 23. We have renewed focus for each domain and increased interest now in security and safety, currently partially handled by SG12. Please join us for games, embedded, finance, linear algebra. That spreadsheet is accessed through this Google link. Okay, and I think that is it. So we have only about 2 minutes left. So I'm going to endeavor to try to answer a few of these questions. And I'm going to capture the rest of these questions, and so that I can so I can answer them later. So what error handling techniques do you use in C++ for embedded systems? We use both error handling techniques using system error. There is actually an official system error, not errno. That's in C since C++ 11. Look it up; it's there. And we also have been working on, in some cases, you do use exception handling if you can determine that it has low exception cost. But right now, there's much debate, and that's why we have a work group measuring the effects of exception handling and figuring out a way to give guidance. It is a big topic. It's a big topic not just here, but in concurrency as well too. So we do want to make sure that we have something. I'm very excited about this new project where we're looking at how C++ exception handling can be implemented as stack-based, which, by the way, is kind of what deterministic exception is kind of all about as well too. So these are promising futures that I think that will work for embedded systems. Second question, is the C++ memory model we now have well suited for the embedded field? Very good question. Some of it, yes, some of it, no. The embedded system sometimes might have accelerators, graphics, GPU units. That memory model is not enshrined in the C++ memory model right now because C++ doesn't know about accelerators. But in reality, we know that DSPs and accelerators and machine learning AI processors exist in the world. So what happens there is that there are other models that are being adapted, that are in the wing, that are adapted. Vulkan and OpenCL just recently built a beautiful GPU type of programming model, memory model, that is ready to go in, and we have to look closely at that when we're ready to accept some of these models. Now, I know we're almost running out of time, so I think that I'm going to have to stop here. I'm going to capture the rest of these great questions and use it to put it in either another talk or do it in SG14. If you guys want to join SG14, I would just say that it's an outreach group. You don't have to be a ISO or national body member to join. Go to isocpp.org, go to forum, find out how to join SG14, and come on our future calls, and we'll definitely discuss some of these issues. And I'm going to hold these questions in bay because we have a fireside chat, I believe, this afternoon where I'm going to be part of. well, you're going to ask some of the limitations about, discuss some of the issues with embedded. So we can definitely reuse this. And if we keep these questions here, we can definitely reuse them for this afternoon. Okay, thank you. Sorry, this is a bit of a fast talk, but I hope that I conveyed enough information to help you guys move your projects from C to C++ in embedded programming. Okay, thanks. Cheers. Bye-bye.